So looking at page 36, the question here is what if you have a gap between the given area and the axis of revolution? All right, so we're looking at the region R between the graphs of y equals 1, y equals the sine of x. So let's get a sketch of that. Okay. So here's y equals 1, or at least an attempt at y equals 1. Here's my y equals the sine of x. Now we're only interested in going as far out as pi over 2, which would be right here. And this would be 0. So the region between y equals 1 and sine of x would be this piece right here. We want to know what is the volume of the solid obtained by revolving that around the x-axis. All right, so very easily with the disk method revolve that around the y-axis, but around the x-axis, different story. All right, so we have some adjustments that need to be made. So let me just copy this real quick and bring it in somewhat. Alright, so I'm going to get rid of a lot of this stuff. Because this is the piece that we're focused on. Alright, I'm actually going to pull this little scribble scrabble out. I kind of went a little too crazy there. There we go. Alright, so if I wanted to, I could create a rectangle to get me to the sine function. And I do want to, so I'm going to do that. And we learned previously that we could spin that around the axis. And that would get us a solid. The problem is it would get us the wrong solid. All right. So we don't want this. But what we could do is get another rectangle all the way up to that horizontal line and spin that around also. And subtract the two. And so what it would do is it would create a cylinder. Alright, so that purple would work its way through this whole region here, getting us everything from -1 to +1, and going into the third dimension, obviously. But then what we would do is bore out the stuff that we don't want by figuring out the volume of the red. So get the purple, subtract from it the red. So what we're going to do is we're going to find a pi r squared, starting at 0 and going to pi over 2. I'm going to call that capital R, d something. And from that, we're going to subtract off a pi r squared, this time lowercase r, d something also. That something, I'm going to get a fresh new color on board here. And that d something is associated with the thickness of each of these slices, which is going to be a dx in both cases. So it's just a matter of determining the r, which we can do right away, because the radius of the big, that capital R, is going to be, well, they're both going to be y values because they're distances from the x-axis to a point in space, but particularly 1 unit away. All right. This other one, get it in red. That's our lowercase r, and that's equal to the y value, which is sine of x. All right, so in both cases, we're integrating with respect to x. So it's just a matter of replacing the capital R with a 1. And the lowercase r with a sine of x. Alright, so everything else can just get popped right in there. I just realized I didn't put a pi over 2 here for the upper bound of integration. Apologies for that. That should have been a pi over 2 all along. Alright, a pi here, a dx there, a power of 2 here. And if we put this in our calculators, we should end up with, well, if we put it in the right way, we will end up with the correct volume. It's just a question of will I put it in the right way? Hopefully. All right. Now, the first piece, though, maybe you don't put that in the calculator because that's constant. All right. And we learned a while ago that if you take the constant and multiply it by the difference between the bounds, that's a nifty shortcut for evaluating the integral. All right. So pi times pi over 2 is going to be pi squared over 2. Okay, so there's that. Also, this is a cylinder. A circle with height is a cylinder. Pi r squared h is the volume of a cylinder. So you could put that information in. You know, we have the r value, the radius of the cylinder is a 1. So pi times 1 times the height, it's a height that's oriented sideways, but that's the height of pi over 2. So pi times pi over 2 is pi squared over 2. So we can get it that way also. All right. Now this other piece, we'd actually have to use some techniques of integration that we haven't covered yet if we were to do it by hand. Fortunately, we don't have to do it by hand. So math 9, from 0 to pi over 2, pi, open it up, sine of x, close it up and square it, and pop in an x here. Sometimes I like to do it without the pi and see if it gives me something cleaner. Not so much. Maybe it's a square root. Yeah, sometimes I like to see if I can sneak an exact value out of it, but not the case here. All right, so it's this subtracted from pi squared over 2. So what I'm actually going to do here is just go back and tuck in the pi squared over 2. Insert it, second delete, insert. Just make sure everything is the way it ought to be. Hit enter, and we get our result. Huh, interesting. Which is exactly the same. Alright, so if that's the case, then these two values must add to give you that, in which case whatever this integral is needs to be half of that. So we can investigate that real quick. Well, what do you know? So as it turns out, now I just kind of stumbled upon this, but you know, sometimes that happens. And this is again without having to use techniques of integration, especially since we haven't covered them yet. Pi squared over 4 just kind of emerged from just observation of what, you know, came through from the calculator. I am going to just go through it quickly on Desmos. So I'll put it in its pure integral form. What I'm going to do though is I'm going to kind of even go further back and put a function of x as 1, a function of x as sine of x. What I'll do is kind of work with this in more general terms rather than trying to type the function in again and again, you know. So we need to integrate over the interval of 0 to pi over 2. So what I'm actually going to do is I'm going to let a equal pi over 2. And I'm going to integrate, I'm going to set up my integral from 0 to a, just less typing, type in the pi over 2 once. All right. And so we need a pi times f of x squared dx. And then from that, we're going to subtract off this, really the same stuff, just with a g. And there it is. And, you know, the benefit of doing it this way is if we change a up here, then it'll change the integral down there. So we can, if we wanted to, we could let a be equal to pi and get a different area. I'm sorry, different volume. You know, so a lot of different options here. Regardless, we're able to verify our answer. All right. So what I did here is I copied and pasted the rule just to kind of show you what it would be in its most general form. All right. So over the interval of a to b, you'd have pi r squared d something minus pi r squared d same something. All right. But you'll notice that we have a common pi and a common integral. All right. So the only thing that's actually going to vary from one to the other is going to be the radius. All right. So I could factor out a pi from the whole thing. So we'd be looking at over a to b an r squared d something minus integral over a to b r squared d something. All right, but since it's the same set of bounds and the same variable of integration, this is the reverse of the sum difference rule for integration, which would tell us that all we would have to do to get the most general form would be to take the radius squared for the outer region, or the outer function, and subtract from that the radius squared for the inner function, and integrate with respect to the appropriate variable. All right. So that's actually going to be our general rule. All right. So I'm going to put all this stuff in here. But now we have a fresh new rule that we could use from here on out, in theory, simplifying things. All right. So the example below, the region enclosed by the graph of y equals x squared. All right, so y equals x squared, and x equals 2, the x-axis is revolved around the y-axis. All right, so this is an ordinary parabola, parent function. X equals 2, and it's going around the y-axis. We have the coordinate 2, 4 here, because again it's the line y, or the curve y equals x squared. All right, so spun around the y-axis. So we're going to have same idea, except organized horizontally. We have the outer rectangle, or the rectangle corresponding with the outer function and then the rectangle corresponding with the inner function, essentially being the piece that we don't want. All right. So we use this to just kind of whittle away the part of the cylinder that we don't want. And when we do that, what we'll be left with is what we do want. All right. So the thickness here is going to be a dy thickness. So if I use my fresh new rule here, it's just a matter of saying, okay, where am I starting? Y equals 0. Where am I ending? Y equals 4. All right. So going from, so we get the pi in the front, going from 0 to 4, the outer radius, well, that's a constant radius. It never changes. It's 2 in all cases. So 2 squared minus whatever this x value is. All right. So 2 squared minus x squared, where x is associated with this function. Well, we know that y is equal to x squared. If I take the square root of both sides, I'll get x. X is equal to plus or minus, got to get the equal sign in there first, plus or minus radical y. It's just a question of, is it the plus or is it the minus? Well, if we're looking at the inverse function, if I want the positive, so positive for an ordinary function would be above the x-axis, negative would be below. For an inverse, the roles change, so x becomes y, y becomes x. So above the x-axis corresponds to quote unquote above the y-axis, which is really to the white of the y-axis. No, to the right of the y-axis. Apologies for that. So we're looking for just the positive in this case. So therefore, x would be equal to the square root of y. That being said, got Desmos. Oops, didn't want to do that. So x equals the square root of y. Take a look, it's the part we want, so pretty comfortable that we just selected correctly. He chose wisely. So 2 squared minus the inner radius squared, which is x, which is the square root of y, squared dy. All right. So it's just a question of, all right, well, how do you want to do it? Well, this one's not too bad to do by hand, but again, you don't have to, so don't feel obligated, even if it's not too bad to do by hand. Don't feel obligated to do it by hand. And just think of it this way, because there are some people that are kind of stuck with the idea of, well, I've always had to do it by hand. What about next course? I might have to do it by hand in the next course. I will say that's possible, and more likely than not. What I will say is, as it applies to this course, I'm gonna get you. I'm gonna get you with doing it by hand before it's all over. In plenty of instances. So don't force it to happen before it needs to happen. Right? Take advantage of the situations where it doesn't need to happen, because I gotta tell you, I factor that into the way I design my tests. All right. So when I decide, all right, I'm gonna put this problem on a test, I do it with the idea in mind that, okay, well, this one's a quote unquote easy one. All right. Now, it may only be easy because you're able to do it using a calculator. Right? If you had to do it by hand, it might be the world's worst problem. All right. So, I'm encouraging you to use a calculator for this stuff, but more than that, I'm kind of flat out telling you to do it. All right? That it's in your best interest to do it. All right. Also, the skills associated with the calculator are required. So it's not a matter. I want to make this perfectly clear. It's not a matter of preference. All right. You can't say, well, I prefer not to use a calculator. You have to use a calculator. You don't have a choice. All right. There will be questions on assessments that are designed to test your ability using technology. All right. Where you do have a preference is whether you want to use Desmos or the graphing calculator. That's a different story. All right. There's pros and cons either way. I don't want to spend your money for you, so I let you decide that on your own. All right. But I mean, it is important to understand that you can't just say, well, I'll do everything by hand. You'll never finish a test. All right. So keep that in mind. Anyway, about 25.133. Units cubed. Now, again, back to Desmos. One of the benefits of using Desmos, aside from just it looking nice, is the notation. It handles notation very well. All right. So what we can actually do here, and I'll show you very quickly, and I'll actually save this up on Blackboard for you. All right. So if we want to say, okay, we want the washer method. We can put this in the most general form that we can think of. All right. So if we want to, what we can say is, all right, we're going to let f of x be the outer function. Use quotes to type in notes. Let g of x be the inner function. A little too crazy there with the ends. Inner function. And so what I can actually do is I could generalize the rule. Right? I'll type in a pi. Because I'm a firm believer in, all right, if you're going to use technology as a resource to help you remember formulas, it might also behoove you to have it actually do something with the formulas on top of it. That'd be kind of nice, you know. So not just tell you what the formulas are, but actually maybe run some computations for you. All right. So function, integral, going from a to b. All right. And then I would have it say, all right, well, we know it's the outer radius squared and the inner radius squared. All right. So the outer function is typically the outer radius. All right. Maybe you make a note of that. Same thing for the inner. So what I could say here is f of x, that's my outer, squared, minus, I tend to go a little nuts with the parentheses, but that's just out of paranoia. All right. Oh, didn't need an extra one. Perhaps too paranoid. But I also like to have another set of parentheses around my integrand. So, and then d, ooh, geez, which one is it? D this, d that? Well, if I'm saying f of x and f and g of x, then it's going to be dx. All right, and so I would need to type in some function f of x. And I would need to type in some function g of x. But doing that and having sliders for a and b would get me what I needed. But the thing is, this is only going to get me what I need for vertically organized rectangles. So I could just do this whole thing again, just with y's instead of x's. All right, but this is a little bit of a taste of how you would go about doing that. So what I'll do is I'll put in maybe the first example. The outer function was 1. and the inner function was the sine of x, and the a value was 0, so I'll slide to 0. And the b value, I mean, you're not going to slide to pi over 2, but you can type in, if you click on it, pi over 2. And it gives you the value that we came up with earlier. All right. So why not do the same thing? I still have it up on my screen here. Why not do the same thing with the g function, the horizontally organized rectangles. So I'll say washer method for vertical rectangles. I'll save this. All right, so I got my calculator going here. It's looking pretty good. All right, I got to log in, I suppose. Probably a good idea. So let me save. I'll title it. So we're good there. And so now what I can do is the same thing, but for horizontal rectangles. So f of y would be my outer function. G of y, inner function. It's going to get confused over what I have here, but I'll tackle that in a minute. I just want to change the notation and things like that. I typically like to switch it up for the bounds, C to D. Most people do that. So I'll make this a D and this a C. All right, and this would be f of y, g of y, dy. And now I'm just going to test it real quick with these functions for the problem we just completed, which are 2 and the square root of y. So 2 and the square root of y. And that went from 0 to 4. So let me make that the slider again. You just type in a 0 to default it back to the slider, and then slide it over to a 4. And that's what we got. All right, so now what I can do is I can save this. I'll just kind of hang on to this example. I'll take this and, oh, I want to get this title. I want to save it as horizontal rectangles. And now I have 2 fresh Desmoses ready to rock and roll for another example. All right, so that's a pretty good benefit of having Desmos or using Desmos. All right, so did we need to do that for this solution? Of course not. We finished this problem a few minutes ago. All right, but in terms of getting something that'll be useful over and over again, we just accomplished something very nice.